As we begin our next unit on gases, let's think about the three forms of matter. We've encountered solids and liquids regularly as we've been solving different chemical problems and looking at stoichiometry, but now we want to start to consider gases. And whenever we think about gases, we want to think about, okay, well, we breathe gases in and out every day, and it's more difficult to see gases because they tend to be transparent, but every now and then we'll see a gas that does have a different color, or we can see the vapor that's being formed. Like if you're boiling a pot of water and we can see the water going from the liquid to the gas phase, we can see that vapor. So gases are actually a lot easier to deal with in a chemical sense because they behave independently of each other. We will expand on this more and more as we go throughout this unit, but right now the key point to think about is that gases do behave independently of each other. So if two gases are moving around, we can think about that they can interact physically with each other, but we aren't going to be worried about the chemical reaction of them just yet. So let's think about the gases on the periodic table. So we have our homonuclear diatomics. So we have nitrogen, we have oxygen, fluorine, chlorine, and hydrogen. So those are some of the homonuclear diatomics that we would encounter. But we'll also encounter noble gases. And these are the most common gases that we will encounter until we start to deal with molecules. So let's go ahead and look at a table that shows the composition of dry air at sea level. So here what we have is a list of all the different constituents of the air, the percent by volume, and then the percent by mass. So what we can see here is that nitrogen and oxygen account for more than 99% by volume of dry air that you would typically breathe in. What we'll see after this is that argon makes up the most of the remaining 1%, and then there are just trace amounts of carbon dioxide, neon, helium, methane, and krypton. So there's just trace amounts of some of the noble gases, carbon dioxide, and methane. One of the key things that you should think about, though, is that CO2 at its present value is at 385 parts per million. Okay, but if you think back to 1850, it was originally 290 parts per million. So what's happened over the last 175 years? Well, that's when the Industrial Revolution started. So we can see that there is a definite impact of modern society on the concentration of CO2 in air. So now what I'd like to do is go ahead and let's compare solids, liquids, and gases. So are solids heterogeneous or homogeneous? Okay, well, solids tend to be heterogeneous whenever we find them. Okay, so an example of finding a solid would be if you are mining an ore. Okay, so whenever you are mining an ore or finding minerals, you don't obtain a uniform mixture of carbon and silver, for example. Okay, what about liquids? Well, let's think about if we have a mixture of liquids. So we aren't talking about having pure water, because then that would be homogeneous. But if we think about a mixture of water and oil, okay, so water and oil will give us a heterogeneous mixture. Okay, so solids and liquids tend to be heterogeneous, or at least in what we're looking at right now. But as we start to consider gases, gases will actually be homogeneous. If you give a sample enough time, gases will reach an equilibrium that is uniform throughout the entire mixture. So for example, what I mean is this. If we have a beaker here, and then let's say that we were introducing a gas, so we have a hose that's pumping gas in, and it starts out that all the gas is right up here in this corner. Well, over time, what we would see is that this gas is going to be distributed uniformly throughout the container. Okay, so this is one of the assumptions that we're going to make for gases, is that gases will exhibit this ideal behavior. Okay, so if given enough time, your mixture of gases will in fact be homogeneous. And one of the other things that we want to think about is the compressibility of solids, liquids, and gases. Okay, so can we compress solids and liquids? Well, let's think about this. You might be able to compress a solid a little bit, but eventually you're going to actually have a physical change. You're going to break the solid, or it's going to break in pieces. Liquids, you may be able to compress a little bit, but not too much. But gases tend to be very compressible. Okay, so for gases, you can think about if you have a balloon, if you can change the amount of volume that gas is occupying as you press on the balloon. So we can really start to shrink the balloon. Okay, so the big thing here for compressibility, gases are compressible and liquids are to a much lesser extent, but we will say that solids are not. So the next thing that we'd like to do is we'd like to talk about some of these properties. Okay, so how do these gases compress? Well, if you go back to that example of a balloon, so what happens as you start to decrease the volume? Okay, so if you're starting to decrease the volume, so if your volume is decreasing on that balloon, what will happen is the pressure will start to increase. And there will come a time whenever the pressure increases too much and the balloon will in fact pop, but we'll see that there's this inverse relationship between pressure and volume. So what we can write is because as pressure is applied, the volume decreases. So we can say that pressure is proportional to 1 over the volume. So they're going to be inversely proportional. So what we'll see is if we double the pressure, then what will happen is we will half the volume. Okay, so those will be inversely proportional. So then why is it that gases form homogeneous mixtures and have the ability to compress? Well, the gas molecules are far apart. So they don't seem far apart to us on our scale, but whenever you start to get down to the atomic scale, what we're going to see is that gases are really, really far apart. And there's very little interaction between the gas molecules. Okay, later on this year we'll get into polar and nonpolar molecules and start to consider some of these interactions. But for right now, we're just going to say that there's essentially no interactions between gas molecules. It's more or less empty space. And because it's all of this empty space with these gas particles in here, this will help explain why we can compress gases. Okay, so liquids and solids are packed really closely together. And they're packed closely together because they exhibit intermolecular forces. And we will talk a lot about this in the next couple of units. But intermolecular forces are talking about how the molecules interact with each other. So if you want to think about the model of the atom, okay, so far we've considered using that plum pudding model and then the Rutherford model. So we can go ahead and use the Rutherford model or the Bohr model for that fact, but we can go ahead and say that we have an extremely small nucleus, okay? And then what we can think about is we have electrons that are going to be spaced throughout, okay? So as we have these electron clouds around here, the atom is more or less empty space. So we can think about this same kind of idea as we start to consider gases, that gases are more or less empty space, and then the elements that make up the gas are just points in space. So that will help us explain why gases have properties the way that they do. So one of the properties is, if we were to consider a solid or a liquid, that much of the volume is actually occupied by the molecules, about 70%. Okay, and that's because there's lots of interactions. And these interactions are from those intermolecular forces we mentioned previously. Okay, but then for gases, what we'll see is that very little of the volume is actually occupied by the molecules. They're primarily empty space. So what we'll see is, we will need to go ahead and introduce a little bit of vocab, but we'll say at STP. Okay, so well, what does STP stand for? STP stands for standard temperature and pressure. And we will have all sorts of units for pressure, but for STP, our temperature for gases will be 273 K. The most common unit that we'll use in here is atmospheres, and that would be 1 atmosphere of pressure. Okay, so but what we'll see here is gases are only about 0.1% by volume molecules. The rest is empty space. So if we increase the pressure a ton, okay, so if the pressure increases by 1,000-fold or more, then what we'll see is that the space is starting to be occupied more and more by the molecules. And as more of the space is being occupied by molecules, there starts to be more interactions, which means that we might not have that ideal behavior anymore. But all the conditions that we're going to consider going forward will be ideal conditions. So the last thing we want to mention before we go on to talk about pressure are some of the physical characteristics. So let's go ahead and compare solids, liquids, and gases. So let's go ahead and say that we have 3 different containers here. Okay, and then in these containers, let's go ahead and drop a solid container here. So we have solid being put into this container. So if we put a solid in the container, it's going to maintain its shape. It's not going to take the shape of the container. It's just going to sit there. All right, if we take a liquid and we start to fill a container with liquid, what we'll see is that the liquid will actually take the shape of the container. Okay, so we might put in something that looks like this, or dump it from a cup that looked like this, but then it's going to take the shape of the container. But if you put a gas in a container, the gas is going to end up giving us a homogeneous mixture throughout the entire thing. So some of the results of this will be, again, that gases will give us a homogeneous mixture. They'll mix evenly and completely whenever they're confined in an area. But the density of the gas, will be much lower compared to that of a solid or a liquid. So next time we'll go ahead and start to talk about pressure, and then we'll move on to some of the gas laws.